Let's review what it means for a function to be continuous at a point. So let f be a function and c a real number, then f is continuous at c if the limit as x approaches c of f of x equals f of c. So that's continuity at a point. We can also define continuity from the right and from the left. So if f is a function and c is a real number, and then we say f is continuous from the right at c if the limit as x approaches c from the right of f of x equals f of c. Remember that little plus sign, superscript plus sign, means that we're coming from the right. And similarly, we can define continuity from the left. Let f be a function and c a real number, then f is continuous from the left at c if the limit as x approaches c from the left of f of x equals f of c. And again, we have a superscript minus sign this time to denote coming in from the left. Okay, we can also define continuity on an interval. Up until now, we have just been talking about points. What about on an entire interval? So let f be a function and suppose that f is continuous at every number in an open interval ab. Then we say that f is continuous on that open interval ab. And there's two special cases I want to look at. First, what about a function that's continuous everywhere, like f of x equals x squared? So that would be just our basic parabola here, and we see that the parabola is continuous everywhere, so we could say it's continuous on the interval negative infinity to infinity, or another way to say that is just say it's continuous everywhere. And then what about endpoints? Consider something like f of x equals the square root of x. So here's a graph of that. It's just our normal square root graph, and this time we see that the function stops here at 0. The domain is 0 off to infinity. What about this point right here? Well, if we're at the endpoint of a domain, then we treat this using continuity from the left or from the right. So in this case, we would say that the function is continuous on the interval 0 to infinity, including the 0 here, where that 0 is taken to mean, in this case, continuity coming in from the right. Let's look at an example. How about the function f of x equals x minus 2 divided by x squared minus x minus 2? So the first thing I might want to do is try and factor the bottom, so I can rewrite this as x minus 2 over, and let's see if it factors. So I could put an x here and an x here, and I would want two numbers that add to be negative 2, or I'm sorry, multiply to be negative 2 and add to be negative 1. And it looks like it does factor as x minus 2 and x plus 1. Okay, and then we see this factor of x minus 2 would cancel out. So that tells us that at x equals 2, the graph must have a hole. And we still will have a factor of x plus 1 in the denominator, so that tells us that at x equals negative 1, we must have a vertical asymptote. So both of these things here, the hole and the asymptote, are places where the function is not continuous. So I could say that f is continuous on the following intervals. So f is continuous on, starting from the left, negative infinity up to negative 1, not including negative 1. And it's also continuous on the interval from negative 1 up to 2, not including the negative 1 or the 2. And finally, it would be continuous from 2 off to infinity. We can verify this graphically. Here's a graph of the function, and we see that indeed it is continuous here up until we get to negative 1. And this is an infinite discontinuity here, where we have the asymptote. And then it's continuous again up until 2, where we have a removable discontinuity. And then it's continuous off to infinity. Here's another example. Consider the function f of x equals, and its piecewise function, negative the square root of x squared minus 4 if x is less than negative 2, and x squared if x is greater than or equal to negative 2. And I'll give you the graph for this one first, since this one's a little more complicated. And from the graph, we see here's the negative square root part, and then we have an open circle here. And then here's our x squared starting with a closed circle, and then there's our parabola. So we see that negative 2 is where we have a jump discontinuity. That's where the problem is going to be. So at x equals negative 2, we have a jump. So let's do the intervals of continuity here. So this function is continuous on, so if we start from negative infinity, and go up to -2, we see here that we have an open circle here, so we don't want to include -2 on that interval. But if we look at the other intervals, starting from here and then going off to positive infinity, we do want to include the -2. So this is continuity coming from the right here. This is continuous from the right at -2. So I could say -2 with a square bracket off to positive infinity. Let's look at one last example. It's another piecewise function. F of x equals the square root of x plus 3 if x is less than or equal to 6, and the absolute value of x minus 9 if x is greater than 6. So again, we have a square root function, but this time we do have to worry about the domain, because we have the square root of x plus 3 if x is less than or equal to 6, but we know that if we go less than -3, that's not in the domain anymore. So when we're at x equals -3, that's an endpoint here of our domain. So that's something we need to consider. We might have to use continuity from the left or from the right for that. And then we should look at what happens at 6. So at 6 here we have 6 plus 3, that's 9, square root of 9 is 3. And for the absolute value, 6 minus 9 is -3, but absolute value is 3, so they do actually match up at 6, so that's not a problem. And absolute value graphs are going to be continuous everywhere in their domain, so I think the only problem we have is the endpoint to worry about. And since this is a graph that has a square root that's kind of going off here to the right, we know that this is going to be continuous on the interval from -3, including -3, off to infinity. And we can look at this graphically and see that indeed, if we look at -3 here, it is continuous off to infinity. There's a little weird corner here, but it's still continuous. And then we have the rest of our absolute value graph.